Okay, welcome back to another video lecture for High School Algebra 2, Section 1.3. And in this section, we're going to be talking about inequalities, whether those are multi-step or compound, and then later on we'll get into the concept of an absolute value inequality, which is just a multi-part or compound inequality. So now that we've covered some of the prerequisites, we notice that one of the uses for Algebra 2, we had equations in the previous section, and these are statements that two quantities are equal to each other. Well, if two quantities are not equal to each other, then one quantity must either be greater than or less than another quantity. So this is where the idea of inequalities comes from. And specifically, the reason why we study inequalities is because if you notice in the very first section where we talk about functions and their domains and ranges, we can tell a lot about the properties of a function from its domain and its range. And inequalities are used very often to express the domains and the ranges of certain functions. Some functions like straight lines, which we've been dealing with to this point, are very nice because you can plug any number into them and you can get any number out of them. So their domain and their range is all real numbers. But if we have to take the time to state that certain functions have a domain and range of all real numbers, then of course that hints that there are some functions that do not have a domain and range of all real numbers, and we require inequalities to be able to express what the domains and the ranges of those particular functions are. Now, inequalities exhibit all the properties of equality with one small exception, and that is when multiplying by -1. And so a lot of times teachers like to shorten this to say if you multiply or divide by a negative number in an inequality, then we must reverse the direction of the inequality. So what exactly is an inequality? Inequality makes use of the symbols greater and greater equal and less equal. And then a lot of times we're going to be asked to draw inequalities using the number line because of what it is that they represent. So an inequality, like in a statement in an equation, we got that x equals something. Inequalities can be true when you have a bunch of different numbers plugged into them, just so long as that number is either less than or greater than a certain amount, depending on the inequality. So when we draw the solution for like an equation, say we have our number line and we get to a final statement x equals to 3. If this is 0, then we have 1, 2, 3 over here, and so we would simply put a dot at that 3, and that represents our solution to an equation. When we change this equality symbol into one of our inequality symbols, either greater thans or less thans, let's say we did x is less than or equal to 3, then that means we can plug any number that is 3 or less into the inequality to make it say something which is true. So inequalities on a number line get this kind of shaded in graph of their solution because they represent any number less than or equal to 3. So 3 or less are all solutions to this inequality. So it's important to note that in these graphing number line sorts of questions, basically we will be graphing those on the number line every single time we solve an inequality until we're familiar with what they represent. So it's important to note that we have two different distinct kinds of inequality. We have the so-called strict inequalities, which are like the greater symbol or the less symbol that do not have the extra little line underneath it to indicate equality. And then we have a more loose inequality symbol, which is the greater equal or less equal symbol. And in general, we want for I should rewrite these so that they're on the same line. We want to represent these on a number line with some kind of dot that indicates whether it is a strict inequality, which means strictly less than 3, but not including 3, or if it is a loose inequality, meaning it could include a certain number. So if we have these greater equal or less equal symbols in our number lines, we'll represent these with a filled in dot. And when we have a strictly greater or strictly less symbol, we'll represent these with an open circle on our number line. That's where we put the number that we get from solving our inequality, and then we shade the appropriate direction based on whether it is a greater or less symbol. So it's important to note that a greater symbol indicates that we'll shade the direction to the right of our solution, and a less symbol indicates that we will shade the direction to the left of our solution. Okay, so now I'll pull up an example here. Suppose that we have the inequality 2 plus 3 times 3k plus 3 is less equal to 44. So again, we like to recall, distribute, combine, and solve. Now, notice that before we start solving this, we need to see that when we get our problem statement and we have an inequality symbol, then this will exhibit all the properties of equality except when multiplying or dividing by -1. In other words, multiplying or dividing by a negative, we have to switch the direction of that inequality. And at the end of this video, as an extension, I will provide a proof on why we must do that. Okay, so here's our inequality statement. And remember, we'd like to repeat the mantra DCS because this is going to exhibit all the same properties of an equation, except with the added little piece that when we divide or multiply by a negative, I have to flip the direction of the inequality symbol, meaning it flips from less to greater. Okay, so I'm going to first check the left-hand side, this side right here, to see if there are any distributes, basically numbers that are distributed over parentheses. I see that I have a 3 being distributed through this parenthesis here. That means that the 3 must multiply both things inside of the parentheses. So I'll have 2 plus 9k plus 9 less equal to 44. Okay. Next, I'm going to check the right-hand side. The right-hand side is just a number, so I'll leave it alone. Okay, then what I'd like to do is combine. So on the left-hand side, I'm going to look for terms that can be combined because they are common terms or like terms. So I'm going to say I have these two numbers that are combinable, but then I have this variable term, 9k, that doesn't interact with anything else. Okay, so if I take the 2 and the 9 together, then that will make 11. And the 9k does not interact with any of the other constants. The way that we solve these in the solve step is basically the same exact thing that we did in the equations section. We want to send the numbers to the right and the letters to the left. So I'm going to take 11 from the left-hand side, which will have the effect of canceling off the 11, leaving me with 9k. I did not multiply or divide by a negative in that step, so I do not switch the direction of the inequality. And pay special attention to that. Anytime you subtract a number, that doesn't change the direction of the inequality. It is only multiplying and dividing by negatives that causes that flip to happen. So I did minus 11, but that doesn't change the direction of my inequality. So on the right-hand side, I have 44 minus 11, which is 33. And then remember, once we have a statement of a number times a variable equals to, less equal to, or greater equal to a number, then I just divide both sides by the number attached to the variable. Remember that canceling the number off of the left-hand side does not make 0 when we are doing that by multiplication or division. It makes 1. So we will have 1k, which is less equal to let's see, 33 divided by 9 will end up being 11 thirds. Okay, and that is our solution. Now, one thing that's important to note here is when we solve an inequality, we get what is called set builder notation. In other words, the solution to this inequality is the set of k that is less than or equal to 11 thirds. But what we would like to do is graph these until we're familiar with what these inequalities mean. So here is 0. 11 thirds is a little bit bigger than 3. It's 3 and 2 thirds. So if I mark a place on my number line, here's 3, here's 4, so here's 2 thirds right there. I know that this spot right there where the little tiny mark is, that is where that number actually is in my solution. So does it get a closed or open circle? Well, that is completely dependent upon whether or not we had a strict inequality or a loose inequality. And so the way that you can remember this is if there's that little extra underneath, then you got to do a little extra work by shading in the circle that I put on the graph. Okay, so now we need to determine what direction are we going to shade in from this thing. And it's very easy to remember that all of the less than symbols, they mean left of. So as long as I have the variable here, if I'm following this procedure of putting the letters to the left and the numbers to the right, then this statement will be true. A less than symbol always means left of. So I need to shade the number line going towards the negative direction. Okay, and there's our first example. Okay, let's do one that involves a flip. Okay, so we'll do this next example here, clean up the board. In this example, we will have 4 times negative 3m plus 4 is less than 52. So the very first thing we want to do is look at what kind of equality or inequality we have. So since I see a less than symbol, I know that this problem is going to exhibit all the properties of equality, except that when I multiply or divide by a negative number, I'm going to have to flip the direction that the symbol faces. And then I solve the rest of this inequality the same way we did in section 1.2. So we'll start with DCS. D for distribute. On the left-hand side, I have a 4 distributed into this parenthesis here. So that means the 4 must multiply everything inside that parenthesis. 4 times negative 3 is negative 12, and then 4 times 4 is 16, is strictly less than 52. C is for combine. That means that if I have multiple m terms on either the left or the right, I can combine them together. Or if I have multiple numbers, multiple constants on the left hand or the right hand side, I can combine those together as well. Now I don't have that in this particular case, so that means I'm ready for S, which is solve. Okay, so solving, remember we like to put the numbers on the right and the letters to the left. So I'm going to take 16 from the left-hand side to have the effect of canceling it out. Remember, canceling by addition and subtraction makes that 0, so we'll be left with negative 12m is less than whatever 52 minus 16 is, and that happens to be 36. Then, once I have a statement that a number times a variable is either equal, less, or greater than another number, I can just divide both sides by whatever number is in front of the variable. So I'll divide everything by negative 12. This has the effect of canceling the negative 12 off of the left. But remember, when we cancel by multiplication or division, that makes a 1 and not a 0. So I'll have a 1m, and then I'll have 36 divided by negative 12, which is negative 3. And what I would suggest that you do until you are familiar with this is when you look at your steps, the moment you divide by a negative number, or you multiply by a negative number, we're going to put a star here to count how many times the symbol in the middle has to flip directions. So when I get to m is either less, greater, or equal to -3, notice that I have one star here, which means I have to flip the direction of the inequality one time. So it was facing this way. Now it needs to face this way, making a greater symbol. Okay, so to graph the solution, we have our number line. Here's 0, -1, -2, -3. And notice that in this case, we have a strictly greater symbol. That's this line right here. So when we have strict symbols without the little extra underneath, I do not need to do extra work by shading that circle in. I just place the circle at -3. So then we need to know, does this go left or right? Well, we have a greater symbol. And notice that the greater symbols, when we have followed this technique, putting the letters to the left and the constants to the right, will always mean shade the direction to the right of the circle. And there you have it. Okay, let me see if we have some more good examples here. Maybe one that involves combining like terms. Yeah, one more that involves some combining of like terms, and then we'll move on to compound inequalities. Okay, so this one will have -4 minus, then we'll have 3k plus 1, and that's going to be less equal to 19 plus 3k. Okay. Now, so remember, when we see our problem statement, we're going to look at whether we have an equal or a less or greater symbol to determine what properties it follows. An equal sign would just be all the normal properties of equality. They're the easiest. When we see less or greater, then we know that these are going to exhibit all the properties of equality, but with the exception that when I multiply or divide by a negative, I have to flip the direction of the inequality symbol. So then we're going to do this the same way we did things in section 1.2, DCS, D for distribute. Now this one's actually a little bit tricky because notice that I have a negative here. Anytime you see a minus, it's important to understand that subtraction is not like addition. It is not what we call associative. So for those of you who want a little bit of extension, I would encourage you to go back to notes that you may have taken a long time ago in the 5th grade or do some Google work to figure out what I mean by associativity. Subtraction is not associative, which means that when I see that in a parenthesis, I can't just drop the parentheses and say that that's -4 minus 3k plus 1. I have to distribute the negative into the parentheses. So there is actually a distribute. It's just kind of hidden in this problem. So the -1 is going to multiply both 3 and 1. I'll have -4 minus 3k minus 1 is less equal to 19 plus 3k. On the right-hand side, there is no distribute, so I'm ready for combine. So C for combine, notice that I have two constants on the left and one variable term. So the constants can combine, but remember that variable terms do not interact with constants in any way. So I'll have -3k, and then -4 and -1 together makes -5 is less equal to 19 and 3k on the right. At this point, we're at the solve step. So remember, solving, we want to divide it up. And I want to put the numbers on the right and the letters to the left. So to send the numbers to the right, I can add 5 to both sides, which has the effect of canceling the -5 off of the left-hand side, leaving me with -3k. Notice that I'm adding 5 here, so that is not the thing that I have to worry about, the exception to the property of equality here. So I can just leave the symbol alone. That'll give me 19 plus 5, which is 24, and then plus 3k. Now I want to throw the letters to the left, so I need to subtract 3k from both sides. That will have the effect of canceling the plus 3k off of the right-hand side. We canceled by subtraction, so that's going to make a 0. We'll have 24 on the right and negative 6k on the left. And notice here, again, subtraction does not cause the inequality symbol to flip. It is only when we multiply or divide by a negative number. So if you say subtract, just leave that symbol alone. Lastly, when we have a statement of a number times a variable is either equal, less, or greater than another number, we can just divide everything by the number in front of the variable. So divide by negative 6. Now notice that I said divide by negative 6, so I'm going to put this star here so that I know that I have to invert the direction of my inequality when I write my answer. So we'll have k on the left, we'll have negative 4 on the right, and because of this star, I have to flip the direction of that inequality symbol so that it's now a greater equal symbol. Okay, so there's my answer in set builder notation. On a graph, remember, here's 0, here's 1, 2, 3, negative 4. I have a little extra underneath, so I got to do a little extra work shading in my circle there. All right, and then remember that the greater symbols are the right-hand direction, so I will shade the number line to the right of my number in the graph. Okay, so that's pretty much all that there is to it for multi-step inequalities that have a single inequality symbol. And notice that those inequalities are sufficient for indicating numbers to the left of or numbers to the right of a specified point on the number line. So right now we know that we can put a dot on the number line that represents a solution to an equation, and there's only one dot because there might be only one solution at this point, at least in the multi-step equations that we've seen so far. Secondly, we know that the less than symbol indicates an area to the left, and then we can indicate whether or not a specified number is included in the solution by the closed dot or the open circle. In other words, the strict inequality or the loose inequality. Notice that greater than symbols indicate an area to the right of a specified number. And again, we can include or exclude that specified number by the strict or loose inequality, meaning whether it's a closed-in dot or an open circle. But in your day-to-day life, you might notice that there are plenty of things that are given to you as a statement of a quantity being in between two numbers. So, for example, you will receive a B in the Algebra 2 course if you have a grade that falls between an 80 and an 89. So notice that that's not an equation because you can have any number in between 80 and 89, which means it's some kind of inequality. But it also isn't strictly to the right of or the left of a certain number. Okay, so how would we write something like that? Well, the good thing about inequalities is we have what are called three-part inequalities. This is a type of compound inequality. They represent the word and the word or. And we do these by writing some expression quite literally in between two different numbers. So we have these two less symbols, and then we just put some number on the left and some number on the right. Now, as a little extension here, you might notice that what this actually is saying is that the absolute value of 2x plus 1 is less than 4. Those of you that are interested in this kind of thing at this point, I would challenge you to explain to me why that is true. Okay, So how do you work with the three-part inequality? Well, notice that this is like saying 2x plus 1 is both bigger than negative 4 and smaller than positive 4. So that little verbal trick that we just did is actually the key to solving this type of inequality. We notice that when you have a quantity in between two numbers, it is that that quantity is both bigger than the number on the left and smaller than the number on the right. So I can effectively take what this compound inequality, split it into two regular inequalities like the ones at the start of this video, and then I can solve them the way that I would always solve them. So let's do this left-hand inequality first. I'm going to look at DCS. D, there's no distributing. C, there's no combining. So I'm ready to solve. I draw my line. Now notice that I would like to do letters to the left. So sometimes people find it advantageous in this case to write this as 2x plus 1 is bigger than negative 4. So some people will like to reverse that, but I think once you get familiar with the methods of solving and some of the little shortcuts that you can make in section 1.2, you'll see that this doesn't really actually matter all that much. But I'm going to do it just for sake of consistency. Okay, so we want to send letters to the left and numbers to the right. I can subtract 1, having the effect of canceling the positive 1 off of the left-hand side, leaving me with 2x. Remember, subtraction does not flip the inequality. I have negative 4 minus 1, which is negative 5. And then once I have number times variable is either less, greater, or equal to a number, I can just divide both sides by that number. Now, I divide it by a positive number here that has the effect of canceling the 2 on the left. Remember, when we cancel by multiplication or division, it makes a 1 and not a 0, so we'll have 1x. It was a positive number, so I don't switch the direction of the inequality. And then I'll have negative 5 over 2, which unfortunately is just a really gross fraction. So boom, that's it. That's the answer in set builder notation. But I'm not done with the problem once I've done the first part of the compound inequality, because you notice this is also indicated by the word and in the middle, this inequality. So I have to solve that one too. Now, another thing you might notice is that whatever we did to solve this one, it's the same thing we're going to do to solve that one. Okay, so I'm going to subtract 1 from both sides to cancel the 1. That leaves me with 2x, the less symbol, and then 4 minus 1, which is 3. This is number times variable, greater, less, or equal to another number. So I can divide everything by the number in front of the variable. To cancel the 2 by division, which makes it 1. So I'll have x less than 3 halves. And boom, these two statements are my answer. So how do you graph this? And why did I start with a conversation about an inequality representing a quantity between? Well, notice this one says x has to be to the right of negative 5 halves. So here's 0. Negative 5 halves is negative 2.5. So that's 1, 2, 3. Here's the little dot there. Now notice this is a strict symbol. So the strict symbols get the open circle. That's negative 2 halves, 2.5. And then that's 3 halves, which is 1.5. And notice again, it's a strict symbol, so it gets this open circle. So I want to shade in the area to the right of negative 5 halves, like this statement says. And then I want to shade in the area to the left of 3 halves, like that statement says. And notice that these two shaded regions just kind of converge upon one another, literally giving us a shaded region in between two open circles. That is what the compound inequalities represent. Okay. Now, I'm not going to work multiple examples of compound inequalities for the sake of time in this video lecture. We are already at 30 minutes. But that's fine because in a video lecture format, you can go back and look at the example over and over and over again as many times as you want. Now, in that last example, we represented a quantity in between two numbers. So the example that I gave you was you will make a B in this high school algebra 2 course if you make between an 80 and an 89. So anything bigger than 80 but smaller than 89. What if I asked you what grades would you have to make in order to not make a B? Okay, so there's two sides to that actually. First off, most of us would like to not have a B, we'd like to have an A. So I know that if I make a 90 on up to a 100, that is not a B. But remember, there is also another side to that where our parents get very, very mad at us. And that would be anytime you make worse than a B. So what would it take to make a C, D, or F? Well, anything less than 80, strictly less than 80, so 79 all the way down to 0, would also not be a B. So that can be represented by an inequality as well. Now the difference here is that instead of it being an entire category of things that are all B's, we have two different categories. One of them is better than a B, or you have the possibility of making a grade that is worse than a B. So we could say, what if we had some sort of inequality, like 2x plus 1, that is either less than -3 or greater than 5. This is the kind of statement that we would use to solve for like our grade if we wanted to know what it would take to not make a B. And I want you to think about that for just a second. Pause the video and think about it for just a minute and think about what that would look like on the number line. So far, we've seen to the right, to the left, in between, what have we not seen yet? Pause the video, think about that, sketch what you think the solution set to this is going to look like, then resume the video. Okay, so this type of compound inequality is nice because it is already broken up for us using that kind of funny English language trick that we used on the three-part inequality. Now in this one, we have an or statement. So in an or statement, notice we have two separate inequalities. We must solve both of them. DCS, there's no distribute, there's no combine. We're ready to solve. Okay, so we like, again, letters to the left, numbers to the right. So if I subtract 1 from both sides, that will have the effect of canceling the 1 off of the left-hand side, leaving me with just 2x, a less than symbol, and -3 minus 1 makes -4. And remember, subtracting 1 does not flip the direction of the inequality. Okay, once I have a number times a variable less, greater, equal to another number, I can just divide both sides by the number in front of the variable. That'll have the effect of canceling the 2 off of the left-hand side. And remember, canceling something by multiplication or division makes it a 1, not a 0. So we'll have 1x. This was not a negative number, so we'll have a less than symbol still. And then I'll have -4 divided by 2, which is -2. And I wanted to point out here that specifically I can end up with negative numbers like this. This is totally fine. It is the act of dividing by a negative that causes that direction change. So that does not happen here. Then I have this other inequality. Same moves. I'm going to subtract 1 to cancel the left-hand side's 1 down to 0, leaving me with 2x greater than 5 minus 1 makes 4. Number, variable, less, greater, equal, a number, so I can divide both sides by the number in front of the variable. To cancel the 2 off of the left, cancel by division makes it 1, so we'll have 1x greater than 4 over 2, which is 2. And these two statements, just like on the three-part inequality, are our set builder notation answers. Now I asked you to predict what you think this solution set looks like, so now it's time to check your answer. Here's 0, here's 1, here's positive 2, here's negative 1, here's negative 2. These are strict symbols, which means we get that open circle at negative 2, positive 2. Then notice this says shade the area to the left of negative 2. So I'll go off to the left here. And this says shade the area to the right of positive 2. So I have this area to the right of positive 2. And I hope that you guessed that that's what the solution set looks like accurately. Again, so far in this video, we've seen areas to the left, to the right, in between, and now we've seen outside of two numbers in those directions at the same time. Okay, again, I will not be working multiple OR statements in this video. For the sake of brevity, please feel free to stop, pause, and reverse the video to review any examples that you need to see more than once. Okay.